we've been talking about variants on Turing machines. We talked about non-deterministic and multi-tape Turing machines. And so we want to be able to convince ourselves that Turing machines really are the end of the road. They are the model of computation for real computers. And so let's convince ourselves, or at least just remind ourselves what an algorithm actually is. So an algorithm if we remember, it's just a finite sequence of steps that can be implemented on a typical computer. And I put that word typical in quotes because it's kind of hard to define what a typical computer is. Does it depend on the operating system? Does it depend on the hardware? I can't really define what a typical computer is, but we all know what a typical computer actually is. And so I want to be able to convince all of you that Turing machines are equivalent in power to what we can actually implement on a real computer. So there is an algorithm to simulate a Turing machine, and Turing machines can simulate any algorithm that we can think of. And it's kind of hard to be precise here. And so the reason why we actually have this class is that we can build up these models of computation, and we can establish equivalence to the more informal notion of algorithm that we have seen so far. And so the one model of computation we've seen before is a Turing machine. And surprise, surprise, it was developed by Turing. Alan Turing was a British mathematician, a very famous story, very tragic story. I would encourage you to read up on it. But these machines were developed by Turing in a famous paper on a completely unrelated problem, but these are the types of machines that he came up with in a paper he wrote in 1936. But there was another mathematician called Alonzo Church at the same time who developed something called the lambda calculus, developed by Church around the same time. And there was yet another one called a rewriting system, developed by Emil Post, who was also another mathematician at the time. And one important thing that came out of this was that Church and Post were actually able to see, yeah, our models of computation are just as powerful as Turing machines. And so the one that really did stick after this time was Turing machines, and that's why we're studying them now. And so since we have shown that these models of computation are equivalent, then we can actually kind of say something quite striking about what these machines can do. So something that's very important called the Church-Turing Thesis. And what this is our idea of intuitive in quotes, notion of algorithm is equivalent to Turing. All right, and so let's try to actually convince ourselves that this is true. Can a real computer simulate a Turing machine?
Yes.
Yeah, so you can write a program that takes a Turing machine as input and then implements the states, implements the alphabets, implements the transition function, and the input, and then just simulate the input. So we can actually simulate a Turing machine. What about the other way? Can a Turing machine simulate an algorithm that we can implement on a computer? So this one's a little more difficult. What things do we really need to actually implement an algorithm in a Turing machine? Well, what's the most fundamental thing that we need to do for algorithms? Sorry? I can't hear you. Well, a flowchart, yeah. So we have conditional logic for Turing machines. We just have a state, and it just figures out if we see something under the tape head, then we go to possibly a different state. So we have conditional logic. Do we have loops? Yeah, we do. What about, say, addition? Can we do addition on a Turing machine? If you think no, maybe not, start homework 5. Because that's one of the questions. Can we multiply on Turing machines? Yeah, because it's just repeated addition. Oh, so we can actually do pretty much anything for an algorithm on a Turing machine. So some people say, oh, this is a proof statement. I don't think that this is a proof statement because then I would have to define that word intuitive, which I don't really know how to do. But again, we have some idea as to what an algorithm actually does, and so we can therefore say, if we can make an algorithm on a computer, a Turing machine can do the exact same thing. Okay? Cool. So we've been talking about decidable problems, things that are actually algorithms that are implemented on a Turing machine. But I kind of want to figure out, are there any undecidable problems, problems that cannot be solved on any computer at all, and therefore, by the Church-Turing Thesis, can't be solved on any Turing machine or on any computer. And so if I can establish something about Turing machines, I can establish something about computers. And in order to do that, let's first talk about actual decidable problems in order to get to undecidable problems. So in order to figure out some undecidable problems, we need to talk about decidable problems, which means we should talk about problems that involve machines that we've seen before. So if we can answer something about machines we've seen before, then we can actually get some idea about what decidable problems really look like. And so we need to actually be able to answer questions about machines we've seen before, like DFAs, PDAs, NFAs, all of that stuff. And so in order to run these machines we've seen before on actual Turing machines, we need to be able to present them to Turing machines. And you think, well, a machine like a DFA is just a 5-tuple which has various parameters, and it's not an actual way of writing it out onto the tape to present it to the Turing machine. So we need to come up with something called an encoding. So an encoding is essentially just a way of presenting a machine to a Turing machine. And so what we're going to do is we're just going to agree on some way of encoding a machine to a Turing machine. And so there are many ways of encoding say encoding a DFA to a Turing machine. But I think a really easy one is that we can just separate each of the 5 elements in the tuple with a separate symbol like the pound sign. And so by doing this, then by writing each of the elements of the finite sets here onto the tape, I've given this Turing machine a description of what the DFA actually looks like. And to get a little more idea as to what each of these looks like, let's say that if we expand the section on Q, then we can probably just write it as Q0, Q1, Q2, let's say QL. And so by doing this, then we have actually created a string representation of our DFA. And we can do something similar for NFAs. We can do something similar for PDAs, context-free grammars, all of those things. And so by doing an encoding, then we can actually present it to a Turing machine and then ask questions about these machines. And so what we're going to do is, suppose that this DFA is called M. And so if I want to give a high-level description of a Turing machine that actually asks questions about this DFA, I need to write some way of writing a string representation of this, and I don't want to write this long string every single time. So we're going to write the encoding. So the encoding than symbol, M, right, greater than symbol. And so what these angle brackets represent is the string representation of that machine. And if we wanted to present, say, another string or another machine to another Turing machine, then we can say that the encoding of M and a string W is M, W. And so we can come up with a bazillion ways of how to actually put this string alongside this DFA so that we can present it to the Turing machine. But you can think of it maybe as it's after the description of the machine or something like that. We good so far? Okay. And so now, since we have a string representation of this machine with this input, now we can actually answer some questions about what this machine can do, or ask questions about the machine itself. And so now we're going to talk about some decidable problems. So the first one that we're going to talk about is something called A DFA. And so what is this? It's the set of all M and W descriptions. So it's the set of it's the set of all M and W such that, well, we got to ensure that M is a DFA. If I don't ensure that it's a DFA, then we're already toast. And what do you think that A represents? It seems like acceptance, right? And so I think I kind of want to have this string be in the language of the machine. So W is in L of M. And I want to claim that this problem is decidable. Is Turing decidable? And so now I got to come up with a high-level algorithm to actually solve this problem. Given some arbitrary pair, M and W, I got to ask the question, is W in the language of the DFA? Something that we've seen before. And so I got to come up with an algorithm. So on input, M and W, well, what's the first thing that you do in any program when you're presenting some arbitrary input? Well, I got to check if the input is actually a valid input. If it's an invalid input, I have no use actually touching it anyway. So if I can verify that M is not a valid description of a DFA, then I can just reject immediately. So we usually write this as step 0 because we just assume that you take care of the input already, and we don't need to write this every single time. So if M is not a valid DFA, reject immediately. Okay? So now, after this step, we have ensured that the machine is an actual DFA. So what do I need to do now? Well, I want to check if the string is in the language of the machine.
How would you verify that it is a valid DFA?
So there are many ways that you can do that. You can ensure that it's actually this 5 tuples separated by number signs is one way. And you got to ensure that the transition function's total. So for every pair of states and character from the alphabet, we have a defined state. So it really depends on the description, but I claim that we can actually do that. It seems very plausible that we can do that. But how do I check if a string is in the language of a machine? Just simulate it, right? Could that run forever? No, because we always eat a character of the input at every single step. So let's try that. So run M on W. And since it always halts, it always halts. It always says accept or reject. So if M accepts W, then what should we do? Then we should accept ourselves because we're trying to solve the acceptance problem. Then accept if M rejects W or does not accept W, then reject ourselves. Okay? This seems like an intuitive way of actually trying to solve the acceptance problem. It's just checking if the input is valid, which we can do in a finite amount of time, then simulating the machine on the input, which also takes a finite amount of time. Then we check if the last state that we were in is an accept state. If it is, then we accept. If it isn't, then we reject. Okay? That seems pretty simple. So now, let's bump it up a little bit. So if we talked about A DFA now, what do you think is next? I think we should do NFAs now. So the next problem is A NFA. And you won't be disappointed to know that it's also M and W. But now M is an NFA, and W is in its NFA. So how do I claim that this is decidable also? Could I just simulate this NFA on this input? I don't think I can because I want, well, even if I use a non-deterministic Turing machine, then I could, but I want to stick to the realm of single-tape deterministic Turing machines. So I can't simulate non-determinism here. So how can I actually avoid that?
Convert it to a DFA.
Ah, we can convert it to the DFA with the power set method, right? Ah, so does that take a finite amount of time? Yeah, because the number of states that we make is only a finite number larger than the original NFA. Okay, so on input MW, where I say where M is an NFA, that's the step 0 that we inferred before. So M is an NFA. And so now we've ensured that M is an NFA. So what should I do first? Convert it to a DFA. So convert M into an equivalent DFA, I'm going to call D. So D is an equivalent DFA for this NFA. So now what do I do? Oh, I can just say, do almost the exact same thing as A DFA, right? Just simulate the DFA on the input that's given, and then answer the question of whether it accepts or rejects. But I don't want to write simulate M on W every single time. So what can I do instead? Do I have a way of testing a DFA with an input? Yeah, I already made this A DFA before. So why not just run the decider for A DFA on D and W? So run A DFA on, and now I gotta give it a machine and its corresponding input. So I'm gonna have to give it to the DFA that I just made and the input that I actually had before. So I know that A DFA is a decider from before, so that's all good. So I know it will accept or reject in a finite amount of time. So if A sub DFA accepts, then what should I say here? Then we should accept also because I made an equivalent DFA. So I should say accept here. If A DFA rejects, reject. Any questions about those two problems so far? Okay, so now let's start getting a little further. So if we had NFAs, what do you think is the next one? Well, before I even get to PDAs, we talked about one other one. Regular expression. Okay, so let's talk about regular expressions. So A sub REX for regular expression. So now I'm going to be given the description of a regular expression with some input x equals, Rx, such that R is a regex, and X is in the language of this regular expression. So, what do you think I can do now? I don't have a machine anymore. We have that way of converting back and forth between regular expressions and NFAs. And that was an algorithm, so we can actually make the conversion. So let's do our high-level description again. So on input Rx, where R is a regex. So the first step is, as was suggested, convert R into an equivalent NFA, which I'm going to call N. Oh shoot, now I have to convert it to a DFA and then ask A DFA for whether it accepts or rejects, right? Oh, I can just run A sub NFA because I already showed that that is decidable. So now just run A sub NFA on, again, I gotta give it an NFA with some input, but I have an NFA right here. So I'm gonna give it N with the input that's given, X. And so, since it's a decider, now it says accept or reject in a finite amount of time. So if A sub NFA accepts, what do you think I should do? Accept, good. If A sub NFA rejects, then reject. So now we have shown that A sub REX is decidable because every single step runs in a finite amount of time, and we just converted it to an equivalent NFA, so we actually answered it correctly. Any questions about that? Okay, so now let's do something a little, yeah, sorry.
Why do we care if it's Turing decidable? Like, what is first?
Because Turing decidable means that we can run it on a computer and it halts in a finite amount of time. And at the end of this, we'll actually be able to show that there are some problems that are not Turing decidable. And so one that's actually pretty useful is check if an arbitrary program, so like a C program, will run forever. Check if it will run forever in a finite amount of time. And that problem is not decidable. So by showing that some problems are decidable, and then trying to use the same methods to show that the same things for Turing machines are decidable will not work. And we'll be able to show through these that we can actually show that some problems are not decidable. So that's the main reason for doing this. Any other questions? Okay, so let's do one that's slightly different. So instead of the acceptance problem for DFAs, let's talk about the emptiness problem. So now I'm not going to be given an input, I'm only going to be given the description of a DFA. So we're going to be given just a single machine. So M is a DFA, and since this is the emptiness problem, I want L of M to be empty set. So I want to be able to show that checking whether the language of a DFA is empty in a finite amount of time. And so you may say, well, just keep testing all the strings, and then just check if every single one said reject. If any say accept, then we should say that it's not empty and therefore reject. What's the problem with that approach? There are infinitely many strings. So I need another way. So how can I check then if a machine's language is empty?
See if it has any accept states.
Yeah, so if it has no accept states, then we should automatically accept that. But what if it did? It may have accept states, but they're not reachable. If they're not reachable from the start state, then I can never get to them. So therefore, there are no strings to accept. So how can I check then if a DFA has any reachable final states from the start state?
See if the final states appear in the transition function anywhere.
But the problem is that
On the right-hand side. If there's any incoming transitions, if you're transitioning out of the final state.
yeah, but the problem with that is that I may have a start state that loops on everything, and I may have another unreachable state go to the final state. So that method of just checking whether it's on the right-hand side of the transition function won't work.
Just do a breadth first search through all the states.
Yeah. So do a breadth first search of the machine itself. So I need to convert this into a directed graph, and then ask the question, does breadth first search from the start state ever hit a final state? So that's what we're going to do. So on input, description of M, where M is a DFA. First thing, treat M as a directed graph I'm going to call G. So G is the directed graph representation of the DFA. And so how would we be able to convert a DFA to a directed graph? Just treat every single state as a vertex in the graph, and every single transition, no matter what it has on the transition, as a directed edge between two vertices. So now we have a directed graph, and then the idea is just do breadth first search from the start state. So perform breadth first search from the start state of M if any final state is encountered, reject. So why do I say reject there? Because I hit a final state from the start. There was a way to get from the start state to a final state. And then otherwise, accept. So I want to convince ourselves that this is actually a decider. So can I convert to a directed graph in a finite amount of time? Yeah, we certainly can do that. Does breadth first search take a finite amount of time?
Yes.
Yeah. Well, breadth first search handles that via the coloring on the vertices when you do cycle.
Okay, I don't visit any vertex.
Yeah. Yeah. If a vertex has been visited before, it won't visit again. Yeah. So the problem was there won't be any problem with cycles here. So breadth first search takes a finite amount of time for sure, and checking if any final state is encountered also takes a finite amount of time. So therefore, E sub DFA is decidable. Good with that? All right. And so one more that we want to ask about DFAs is, are two DFAs having the same language even if they look completely different? And so that has applications in like checking your homework if the DFA is actually correct, right? I want to actually ask the question, is your DFA that you give us the same as the DFA that we have? Even if they have completely different set of states, even completely different transitions, do they have the same language? And so that's what we're going to answer next. Okay. So the next problem is EQ sub DFA. And so now I'm going to be given the description of two DFAs. So I'm going to call them M1 and M2. So M1 and M2 are DFAs. And L of M1 is equal to L of M2. And I want to claim that this is also decidable. And so a natural algorithm you would think is just check every single string. If both machines accept, then we should keep going. If at any point a string is rejected by one and accepted by the other, then we should reject. But as we've seen with eDFA, that will take an infinite amount of time. So I need another idea. Well, I don't know whether the two languages have anything in common at all. Maybe they do, maybe they don't. But let's just assume that they have something in common. So let's treat this as the first circle is L of M1, and the second one is L of M2. And so now I want to check, are the two circles representing their languages, are they the same circle? And so how would I check that? Yeah.
The intersection of the two languages they accept.
So that's an idea. Is the intersection the, why intersection the empty set? I'm checking whether they're the same. The thing I want to happen is that their intersection is exactly the same thing as either one of them. So what do I want about this region out here? Well, these are the strings that are in M2's language, but not in M1's language. What do I want that to be?
Empty.
I want that to be empty. Oh, what about this region out here? Do I want that region to be empty too? Yeah, so I want both of these regions to be empty. So therefore, could I say that I want their union to be empty? Yeah, I would say if I can show that the union of these two regions is empty, that must mean that there's no string that is in one of the languages and not in the other. So I want to be able to make a machine that that checks whether this is empty. Do I have a way of checking whether a DFA's language is empty? Yeah, we just came up with eDFA, which is a decider. So let's do this. On input M1, M2, where M1, M2 are DFAs. So now I gotta make, yeah.
Sorry, would you mind explaining that again, how the union will be?
Right. So I want both of these shaded regions to be empty. If I do, then I know that their languages are equal. So therefore, in order to check that both of them are empty, if their union is empty, then both of them are empty. Right. So that's the way to do it.
It's union, not intersection.
Is union, yes, because it may be the case that they're both non-empty, but their intersection is empty. Just happen to be disjoint, yeah. So, yeah.
What's the, because you said the shaded region, what's the symbolic description of the shaded region? Because it's not
Right.
the same as M1 or M2.
Right, so the one on the left represents L of M1 intersect the complement of L of M2. And then the second one on the right represents L of M2 intersect the complement of L of M1. Do we have a way of doing complement on DFAs? Do I have a way of doing intersection on DFAs? Do I have a way of doing union on DFAs? So we have a way to do this. So we make M1 prime such that L of M1 prime is L of M1 which we know how to do, make M2 prime such that L of M2 prime is L of M2. And so now I want to make a DFA that represents the shaded region. So that's just the intersection of M1 with the complement of M2, union the intersection of M2 with the complement of M1. So, let's do that. So, construct a DFA, I'm going to call C, with language. Well, what's the language that I want? It's L of M1 intersects M2's complement. So I'm doing this shaded region right now. So M2's complement is just L of M2 prime. So L of M2 prime. But I also want the union of that with the shaded region over here. But that is just L of M2 intersects L of M1 prime. But I want both of these intersections to be empty. And I do that by doing union, and then I will check if that union is empty. So I can make a DFA for all of them. I can make a DFA for the intersection of two DFAs, and since I have a DFA for both parts, I can make a DFA for their union. It may be a very big DFA, but I can certainly do it in a finite amount of time. And so now what do I ask about C? I want to check, is C's language empty? Oh, do I have a way of doing that? Yes, with the DFA. So now, run E sub DFA on the single machine, because remember it only takes one machine, on C. If E sub DFA accepts, if E sub DFA rejects, reject. And so that's exactly what I want. And so let's just convince ourselves again that this is truly a decider. I can convert a machine into its, I can make another machine for the complement of a certain machine in a finite amount of time. I can do two intersections in a finite amount of time with the product construction. And we can do union again with the product construction in a finite amount of time. And E sub DFA we showed was a decidable problem. And so therefore checking whether it accepts or rejects is also decidable. So I can check if the language, if two given DFAs have the same language in a finite amount of time, which makes it a decider. Any questions about any of that? Yeah.
Is the reason that we have to union, we have to do both cases, like the trivial case where we're checking between a non-empty language and an empty language? Like,
Well,
is there a reason it's not?
I want both of them. I want both of them to be empty. And so if any one of them is non-empty, I want to detect that. And so by doing union, the only way for one of them to not be empty is if their union is not empty either. So if their union is empty, both of them have to be empty for sure. Okay? Yeah, because if one of them wasn't empty, then their union would have to not be empty. Because union, empty set, union, empty set is empty set. Okay? Any other questions? Okay. So, let's do one that's slightly related. And it's very short. So all sub DFA is just a machine, and I want to check L of M is sigma star. And so I want to check now that this DFA that I'm given accepts every single string. So how do you think I can do that?
sigma star and run the previous line.
I could run EQ DFA. Could I make a DFA that accepts every single thing? Yeah, I can do that. So there are actually two ways you can do this. So on input M, where M is a DFA, construct a DFA D with L of D equal to sigma star. And since we showed that EQ DFA was decidable, then we can actually just run that out with them before. So run EQ DFA on, well, I gotta give it both machines because EQ DFA takes two machines. So on M and D. If EQ DFA accepts, if EQ DFA rejects, reject. So we just answered a whole bunch of questions about deciding things about DFAs. So we can actually show then that a lot of problems for DFAs are in fact decidable. Any questions about any of these? Yeah.
What would the DFA D look like in this one? The language is sigma star.
So you can just make this a one-state DFA that was an accept state that just looped on everything.
Okay.
So, but you can play around with this and make it anything you like, but I think that's the most efficient way. Good with that? Yeah.
You said there are two methods. What is the one?
Good question. Someone was paying attention. So, what's another way that I can decide all sub-DFA? Complement and then ask the question about emptiness. Yes. So another method is on input and then the rest is the same. Construct. So the machine is M. DFA M prime with L of M prime being the complement of L of M. Then just like we said, run E sub DFA on M prime. And so I'm going to do it a different way and output what E sub DFA said. So if E DFA says accept, we say accept. If it says reject, we say reject. So that is in fact, there are two ways of doing all sub DFA here. Because if a machine's language was sigma star, its complement is empty. If it wasn't sigma star, then there is some string not in it, which means that its language is not empty. So this really does work here. Any questions about any of that? Yeah.
For the other one.
For the first one?
No. If the two machines are equal, can we use Boolean logs to simplify that expression?
I don't think you can very easily. You might introduce more intersections and unions, which would make it take longer, but as long as it's equivalent, that's all I care about. As long as it takes a finite amount of time, I don't care how long.
Are we going to need to know both methods, or both one is what we can just...
I think the most important thing is that you know that all sub DFA is decidable, and there are easy ways of actually showing that it's decidable by just running one of the other machines that we've seen. Yeah. So just the fact that it's decidable is all you need, I think. Any other questions? All right. So let's start doing some problems on context-free grammars. We're moving up in the chain. So we started with A DFA. Let's do A sub CFT. Oh, thanks. I'm new to this presenting thing. So I need to have a context-free grammar and a string. So G is a CFG, and W is in its language. So how do you think I'm going to be able to do that? Well, what about Chomsky normal form? Do we know something about how long strings take to accept in Chomsky normal form? We actually know exactly how long it takes. How long is it?
Finite.
Well, it's a finite number, but what's the exact number? It was a test question. 2 times the length of the string minus 1, except for the empty string, which only takes 1 rule application. So we can actually be able to do this. So, on input GW, where G is a CFG, convert G into a CFG in CNF, which I'm going to call G prime. So G prime is just the result of converting G into CNF. So now we have 2 things to worry about. If W is the empty string, then we need to check what? What's the only way that the empty string could be derived in CNF?
Stop state.
From the start variable generates empty string. So let's do that. If W is in fact the empty string, and S is S derived empty string is a role in G prime, except. But what if S goes to empty is not a rule, but W is empty? But we should reject because there's no other way to generate the empty string. So, if W is in fact the empty string, and S goes to empty is not a rule in G prime, reject. Note that I didn't say otherwise reject because W might not be empty and we still could generate that string. Okay? So, now I gotta figure out, I know the length of the string of W, and now I gotta figure out which derivation should I do. Oh wait, how do I know what derivation to do? There actually may be many in Chomsky normal form. There may be many leftmost ones because I may have many rules that have 2 variables on the right-hand side of S. I actually don't know. Could we try every single one? It might be a ridiculous number, but could we do it in a finite amount of time? So let's do that. Remember, we don't care about efficiency. So if, construct every way to apply 2 times the length of W minus 1 rules to S, the start variable. Well, if any of them generate W, then we should accept, right? Because there was a way to derive W. So, if any derives W, accept, otherwise, reject. Okay? So, just because we're trying every single way doesn't mean that this is any worse than some other clever method. We're just trying every single way. And there's a finite number of them, and therefore this is a decider. So we'll see you on Monday, where we'll pick up from there.